Okay, so basically to start, I want to talk about like the actual design process because I know in design training y'all learned how to do CAD, and it seems like you guys know that, like you have the CAD part pretty down, and that's very good. Um, but what you don't have right now that I've seen is like sort of context for what sort of things you use and how you integrate those into robot mechanisms. So I just want to give you some of that context. And I'm going to share some examples from previous seasons, specifically for ERC, but I'll also show some FRC robots. And then, ask questions. Just interrupt me at any time if you have a question. I really, would rather you interrupt me than forget your question. So I'm going to start off with the CAD workflow. And this should really be the design workflow because the first part that is most important to me is sketching. And I know not everyone likes sketching. I sort of live by it, like I always make like an isometric sketch like this, just so I get a sense of what the idea I'm trying to build looks like. There's only so much you can get from a top view or a side view. An isometric is get good at drawing isometric sketches because they're not that hard to do actually. You just need like three sets of parallel lines. I mean, if you have this angled plate, there's a fourth set, but that's not really that difficult to do. And then you can see that they translate almost directly into Crayola CAD, which is, I think, has been described to you a little bit by Wesley. So these were the two concepts for ERC 2022. The goal was to intake a ball from the ground and then output it out the side. That was the mechanism goal we had decided after strategy. And so I was thinking of the most simple way to do this. You could have a conveyor that was on the top and that was going straight up. And then if you had this ramp here, it would push the ball towards the left. It would slip on the belt and push the ball out the left side. And so that turned into this CAD concept. You can see we have 2x1 tubing holding this shaft. Anytime you really have a shaft moving, you want it in some sort of box tube. And the most common are going to be 2x1 or 1x1. You'll really never use anything else. If you ever really need to use something else, like you have something that needs 2x2 tubing, that's doable, but it's much harder to get 2x2 tubing than 2x1 or 1x1. And 1x1 and 2x1 have, you guys have seen the KOPs, right? They have like hole patterns. And so you can bolt stuff to them more easily. Um, this design is sort of manufacturable. I mean, it has no plan for where the motor is going to go to drive this conveyor. And this ramp looks like a pain in the ass to make, but it's doable. And then this design here was the sideways conveyor, where the conveyor belts were on the side of the ball and potentially shooting the ball into the goal. And this also had a horizontal bar intake in the front. That was part of the design originally. But when Crayola CADing, I realized, oh, the ball is actually bigger than it was in my sketch here. That's the nice thing about CAD is that everything is true to size as long as you make it true to size. So the ball was 5 inches. You can see that having these wheels here side to side means that if the ball is anywhere within this frame, like it'll hit one of these wheels and the wheels are spinning inwards. So if it hits the outside of the wheel, it'll bounce it inwards. And then it'll bounce between the wheels until it goes up through. Um, and you might notice that the wheels are a little bit wider than the belts at the top. And that's because I wanted a higher surface velocity at the top so that it could sort of feed it in slowly and then shoot it. That's like having a gear reduction, but without actually needing gears, because if your wheels are bigger in diameter, they'll spin faster at the surface. It's just how gears work, basically. But y'all know that, I think. But yeah, so, have some sort of vision. I mean, I don't always sketch everything. Like sometimes I'll just jump into CAD and do an idea, especially when I'm really craving making CAD. But very often I'll stop myself and be like, okay, let me sketch this out because there's always something that you'll learn from sketching it out, and there's always something that you'll help visualize. And then when you're doing the CAD, it'll help you stay true to concept. I mean, these two look very like these two, and that's because these two sketches were made before these two. Um, Nice thing about sketching as well is that if y'all, I mean, most of y'all who showed up here are like sort of design leading, in quotes, your ERC team. And that means you can crank out sketches like this that very specifically show what a design is supposed to do, and then you can assign them to people. So you can say like, okay, one person take this design, one person take this design. And if you give them a sketch, an isometric sketch, rather than just a horizontal sketch, a side view or something, they're like way more likely to come up with CAD that looks like your vision. And having collaborators help execute your vision is very important, because if you're not all on the same page, then you wind up having an incohesive design team. So yeah, I'm gonna go next. So we have Crayola CAD. The basic gist of Crayola CAD is to mock up basic shapes and sort of ensure legality and verify design viability. So legality being like, okay, can this design fit within frame perimeter regulations? And design viability being like, are there any unmanufacturable parts on this design? This ramp might have been an example of that, although it's really just a rectangle, but it's a rectangle mounted at a really weird angle. You'd need like some 3D printed brackets. But overall, you should be checking for design viability and manufacturability. And then you can also rapidly test and iterate lots of designs. So the nice thing again about Crayola CAD, it's sort of like one step above sketching, where here you can crank out an idea really fast. I've gotten good enough at Crayola CAD that something like this would take me maybe 20, 30 minutes. And so you can do that, give it to somebody, and then they have a 3D representation of what they're doing. You know, if you're just sketching things out, you have some dimensional constraints. Like this wheel is 90 millimeters because I knew that whatever wheel we used would be 90 millimeters, and I wanted that size to be accurate. The ball's 6 inches. And this drive base is obviously accurate because it was already CADed. All I had to do was delete this front rail, and we were good. But then Crayola CAD can be basic or advanced, and there's a couple steps in it. So this is Crayola CAD for our 2021 online robot, and we had this intake here. And this intake would pick up a ball. This red belt here would sort the balls. It would like push them forward, and this ramp would hold them. You had to hold 5 balls, and then this shooter shot them out. You can see here, this is, it's not quite Crayola CAD, but it is Concept CAD, where you can see the wheels here are like blocky shapes, and these sort of flapper wheels, they're not real parts. They're just, you know, yeah. And then this motor is just mocked up. It's a rectangular prism in a circle. These plates are clear, so you can see what's going on in there. There's stages of doing CAD in levels of detail and planning, and so you don't always need detail. Like you could probably manufacture a robot from this. The robot would have a lot of jank to it because it would be mechanical members figuring out stuff on the fly, and that's always going to be janky. But you could also do something off of this, and it would be slightly less janky. And then you could do something off of the real CAD this year, which was like every bolt, nut, and screw were CADed, and then the robot is actually going to be fairly, you know, well put together. Ah, it's Toonie. Hey, Toonie. You missed my sketching plug, but you've already heard it. So, okay. So, and actually, I will go through a process later of, I'm going to start with a sketch. You guys can watch me make a brief sketch, and then I'll do like a Crayola CAD, and then we'll leave it there. If y'all are interested in that, I might do that. I do want to show you guys some of these designs though. So I'm gonna, let's see, go here, go to Onshape. Yeah, so these have all been, here we go. So here's the ERC 2020 robot concepting. And that's just this design right here. It's actually both of these designs. So they were in one document, and you can do a lot of this in one document. If you have separate concepts, it's usually better to do them in separate documents, just because, I don't know, it's annoying to do it any other way. Asking for a lot from Onshape right now, but it's doing all right. So you can see here that this is a really simple concept, right? There's like 3 structure parts, these 2x1 tubes, which mount to the side of this plywood board. And in CAD, always, always, always make things the color that of the material they're actually going to be. Actually, not always, always, always. These are blue, but the wood board was very important to me because a big flat piece like this can be made out of several materials. You can make it out of metal or polycarb, but wood was best because it's cheapest and you can screw into the side here. Um, so you don't need like a bracket if you can just put a wood screw straight in here. And we actually wound up going with thicker plywood on the real design than this, which is just, if I click this here and the back there, this is just 1/4 inch. We wound up going with like 3/8 inch plywood. So we probably could have done 1/4 inch. And this doesn't have any motors in it either. You know, like the viability test wasn't that big of a viability test, but I mated this ball to the surface so that it runs up and down the conveyor. And I actually have a cool little configuration panel where it'll choose the ball action, whether it's intaking, which sets it planar to the floor, whether it's conveying, which sets it planar to this, or whether it's shooting, which puts it on a linear path. You can see the shooting puts it on a linear path that goes out the side. So it only ever goes like this. And then if I put this as intaking, it'll go to the floor. So having easy testing and visualization in your CAD is also important. And this is one of the aspects of that. You can see with the second conveyor concept, I didn't really do this one as much. This was Kevin and Reese. Can't remember who was working on this. But yeah, the ball comes up. You can see there's a good amount of interference between the ball and the belt, and you want that because the belt is stretchy and compliant, and you want the ball to come up through it. Now, if we look at this 2020 ERC robot design, this is the more in-depth version of this Crayola CAD, and you can see that this has all the bells and whistles. I mean, it's got hardware. It's got screws to show you where the main board is held in place right here. See, it's got chains. These motors are bolted to this board, and it's got sprockets on the end of those motor shafts. This is 5mm hex coming out of that motor, and the sprocket is on the end of that. And you don't need a bearing for this because the motors have internal bearings. Unless the shaft is like super long, then you should support it on the other end with a bearing. But these chains go down to the sprockets that drive. There's one that drives this one, and there's one that drives this one. Now, I figured you could do it with a geared reduction, but there were two things here. I didn't want to waste, or I didn't see the need for another motor slot. You only got 2 additional motors this year. Now it's up to like 3, I think. But I didn't see the need to use a motor anywhere else, and so I was like, give me more power. It'll make the shooter work better. But also, I figured that tuning the speeds between these two might be useful if you wanted to change where the shot usually went. So we had this hard stop at the back, and that would put us against the wall a certain distance that I calculated the ball would go into the goal. So like that distance was like the ball will go into the goal anywhere if it's next to it up to 2 feet away. And you can actually see in the staging, I put the robot on the field, see if this loads. I put the robot on the field and checked it up against the different game elements. And the field CAD is public, by the way. So you guys, I highly encourage you to do this because it's a really, really easy way to check functionality without actually having to, build a field and make it. That's what CAD is so good. You can see there's a back wall here. This goes up against the wall like this. And then this is launched straight from here. And you can see that's just about hitting the top there. So I calculated this was the farthest distance it could shoot from. And that distance is 8 inches. Now it wound up shooting from, I figured it would shoot from farther than this because of the effects of gravity that's going to pull that ball down. So it would wind up hitting the far edge of that circle and not the top. Oh, and you can also see this one has flappers. They're not properly constrained to the wheel, but you can see this is a bunch of stacked 3D printed parts, and the zip tie just goes in there like that. Um, but these flappers were zip ties with weights duct taped to the end of them, and it was super sketchy. And like, do not get your shins near that. But they did work very well, and it meant that we didn't need a ground intake. And I think for this year's cube, you may need a flappers like this may not work because they're heavier and they're not a circle, but I'll let you guys decide that. Um, and then here's the simplified robot from 2021. You can see we have our shooter and our intake. Drive-based gearbox is represented. Now, I'll let you in on a little secret. This Crayola CAD wasn't actually made before the actual robot. The one I'm about to show you was the original concept CAD. This was made afterwards because I wanted a simple platform to like build new mechanisms on. So we were gonna maybe do a climber, and I wanted to see, okay, where can you fit that climber? I wound up deciding like if you have two climber tubes, you could fit them like here and here. Although that's a little difficult because there's chains here, and I didn't mock up the chains in this mock-up, so you can see there's sometimes a limitation there. But this intake rotated. You know, this shooter, none of the other big things moved, but it was a good mock-up. And then this, I mean, this looks complex. If you isolate any subsystem, it's really not that bad. Look at the index shooter here. So you can see we have this nested sort of rotating hood, and that's just made of two side plates and some shafts. There's actually not even any shafts in here. This wheel was just mocked up as floating because I figured the shafts would be the difficult part. And then you've got these belts that go up here that drive this top wheel, and then down here you've got a motor to run the you know, the wheel that brings the balls into the shooter, and then there was a motor here to run this conveyor belt. And then these parts were actually, this was a fun part to make. Um, it just looks like that. I figured we were going to make it out of bent polycarbonate, and you could do something interesting in Onshape called sheet metal design, where you design this as a sheet metal part, and it'll generate a flat pattern. So that's the pattern you have to cut out, and it'll tell you what bends to make and stuff to make it look like that 3D shape. But explore that on your own. I'm not going to teach it today. Oh, and then these were all the, you might have heard the story of the 88 rivets that I did. That was for all of these backing plates here. So yeah, okay, does anyone have any questions so far about the Crayola CAD process? Sweet, okay. So let's go next to the COTS CAD and imports. So I showed you this design here. So you can't just get parts anywhere. There's actually a set list of parts that are legal for this activity. Assume that if they're FRC or FTC legal, then they're legal for ERC. But you know, the extreme take is that every nut, bolt, and gusset are represented in CAD. You don't always need that, but it's good to have actual products in your CAD because you have to know how you can machine them, and you have to know how they can actually be made and if you can actually make them. So the main site you're going to use for this activity is Rev Robotics. It's what supplies the HD hex motors here. Great little motor, great little gearbox. West Coast Products is, they work with VexPro a lot, and they develop similar products. They're for FRC mostly, but if you need wheels or, you know, tube stock, aluminum tubing, or sheet polycarbonate, West Coast Products and VexPro are great solutions. VexPro also has some motors, but I would encourage y'all to use Rev Robotics motors just because we have those and we're, you know, happy to order more. VexPro motors are way more expensive too. And then Andy Mark has random stuff. You know, if you want to check on Andy Mark, there's a lot of cool stuff there, but they do have FTC things as well. So if you need like a super cheap gear motor, their gear motors are cheaper than Rev's, but they're not as nice because you can't adjust the gear ratios, which you can with the Rev motor. It's super nice. Like you could just swap out the stages. You guys have played with it. You know what I'm talking about. So I have a bit of an example here. I wanted to show you guys some importing and modifying off the shelf parts. So we're going to go into Onshape here. And let's see. And then I'm going to go to VexPro. I'll go to Rev. I have it bookmarked because I'm cool with that. We're gonna look up max 2. Let's see what we want. Let's go to the bottom here. If you scroll to the bottom of the page, there's specs and CAD. And if you download this, and look at that, they have Onshape files. Honestly, a step file is easier to work with. There's also MKCAD, which I'll show you in a second. But let's just go 2x1 light. So download that step file, and we'll take it into documents here. I'm gonna go into, I'll make a new folder. Shop. You think Wesley got, yeah, okay, you all downloaded MKCAD. MKCAD is great. It's mostly FRC parts, which is problematic. Import example. So there's some FTC parts in MKCAD, but it was made for FRC. So I think, yeah, MKCAD was in the curriculum for y'all. But if okay, hold on, I just didn't say what I did. So I'm in a Part Studio here. I'm gonna press this plus and click import. And now I can go in my downloads and I can select this file and I'll combine it to a single Part Studio. It's just one part, so that should be fine. But if you're downloading like a wheel or something, sometimes it's like the tread of the wheel and the body of the wheel as 2 parts. So you want to combine it to one Part Studio, because then you can like make it a composite part or something, make it easier to work with. I'm gonna find myself a little wheel here. Wheel. Let's go with a traction wheel here. Actually, no, the 90mm grip wheel looks cooler. So we're gonna do that. And I'm gonna download it. How do you get different imports into one Part Studio? Very simple. I'll show you. You go like, so delete all here. Here's our import. It's nice. Let's cut it down to length. What length do we want this to be? Like, let's just make this a drive rail. So let's go, I'm gonna click this face, Shift E to extrude it. Then I'm gonna go remove up to face, and then offset distance, and that's the length that the tube is gonna be, which will be 13 if it's a side drive rail. And I'll click this face, and it should cut it right. There we go. Okay. So that's the length I've got here. And I'm going to import my other item here. You can see it's clearly in my files elsewhere, but, and this is where I'm going to want to combine it to a single Part Studio because it would just populate a bunch of Part Studios. And also, if you go to CAD imports here, this is the raw file. Onshape has to process that into a real file. So I'm going to name this Part Studio Rail Mock Up. And we're going to do something called, let's see, is it importing? We're going to do something called a derived part, and that's how you get other parts into Part Studios. And you can actually derive parts from MKCAD, which we'll do in a second. So derived part is in your part menu down here, in this whole menu. It's right here. So I'm going to derive this. Actually, I'll derive both. Yeah, I'll derive this. And that'll bring that in here. And now I have this in here, but look, I can't move it around at all. That's sort of annoying. So I'm going to do something called a transform. If I click on this part, and then I say transform by mate connectors, it's basically a mate. So I can go ahead and put this on the middle, to be honest. And then I'm going to click the origin, sorry. And that will make it go like this. And I think, yeah, that's about how I want it to be. So that's good. And then you can add offsets to that if you want. If you go in this transform and you click on the details for each of these mate connectors, you know, I can maybe offset it so that it's 0.5 over minus 0.5, so that it's centered on the origin. And now I have my part here, and you can see I still can't move it, but it's transformed to a nice place. And I'm going to edit the appearance so that it's silver, because that way you know it's metal. There's no question about it. Now we got our wheel, and you can see here, what's really interesting is that there's going to be 2 parts at the bottom here. You have your tread, And it's cool because these parts are bonded in real life. Oh, it's Ryan Huang. It's cool because these parts are bonded in real life, and you can see how they're bonded. So this just has these flaps here, and then this tread is overmolded. Lights like that, and it just sort of slides in there. You know, you can see like it's got these back things. So pretty neat. It's just like the tread material is poured as a liquid around the wheel, and then it sets. But you know, if I import this into an assembly, it's just two parts, and they're not constrained to one another. So if I do this, it's not really useful, and I don't want to have to click, you know, this, and group every time I want to make a wheel that works. You know, that's a lot of work, and I shouldn't be expected to do that. So I'm going to click both of these parts. I'm going to click down here. No, it's this one, composite part, and that will just turn them into one part. Boom. And you can, you know, have it so that it keeps the old parts if you don't click closed. If you do click closed, it'll maintain everything. And then if I, well, I got rid of the old things. I might actually go into this composite part thing here. And I'm gonna unclick close. That way it keeps the old stuff. So this should be still around, but if we go here and we click visibility for composite parts and we drop this down, you can see composite part 1 is right in there. And so now this moves on its own. This won't move on its own if I delete group 1 here. Actually, I'll right click it and just press suppress. But this still will. Anyway, maybe I spent too much time demonstrating that, but it's very useful. So I'm going to make a quick hole in this part. I just clicked Shift S there, N for normal, and I'm going to make myself a little circle. The thing about VersaFrame and MaxTube is that you really want to make a line like this, because if you look, the center that it will snap to is actually one of these edges, and that's not centered. So I'm going to make a point here. Actually, I'm just going to make a line that goes across, make it a construction line, and I'll just make it super long. I'm going to go down here so it doesn't snap to anything, and then I'm going to click it and press H for horizontal. And then I'm going to make myself a little circle here. I'm just going to make it on this line. Actually, I'll just make it on the end point here. That's easier to snap to. Why does it have the grooves? It's so that when you're machining it, you can just punch right into a hole, and it'll make sure that the hole is in the middle, half-inch offset from the right or half-inch offset from the left. So it's a machining aid. Makes CAD more annoying, but it makes machining better, and so that's why we use it. And I'm going to dimension this to, did I already say 12 mil? I did. When did I do that? I don't remember doing that. Okay, I'm going to go from the edge here. I'm going to make it just away from the edge, and I'll extrude that. Okay, so there's my hole. And if we look at this part, let's go back to our slideshow here. This is the same workflow we just went through. Now, for this lesson, this slide initially came from a lesson for FRC design, but so it used Vex Pro VersaFrame. You can use VersaFrame for this. We have anyway, but Rev MaxTube is a new product actually, but it still works. So you can see, you know, the full length thing imports, then you cut it down to length, sketch a hole, and cut that hole through it. And then I actually made this GIF set showing the machining steps you would need to actually achieve this. So you cut it, you know, put it in the vise, run it through with the portaband, that gets it here. And then you mark your hole and you drill it, and that gets it to here. So it's two pretty simple machining steps. It's important to consider the machinability of your parts when you're doing this. Because, you know, like if you don't have machinable parts, your design can't be executed, and it's very important. So let's see, I was gonna maybe do a little bit of more deriving and importing and stuff, but I feel like you guys get the picture. If I take this into the assembly, I'm gonna make a new assembly. Oh, and here's another cool thing. If you have like a something that you would like to be the title in an assembly, if you have something that you would like to be the face of your document, right click this and say select as document thumbnail. because it just does it randomly if you don't select an explicit one. And I'll put the parts from drive rail mockup, and I'll put the composite part I had here, composite part 1. And now we can just, I very rarely fix things. I don't know how Wesley showed you to constrain parts. Usually what I do is I'll click some center point, and then I'll click the origin, and I'll do what I call an anchor, where I made it to the origin. And that way I know where everything is, and I'll just name this anchor. And now this isn't going anywhere. And then I'll do a quick little revolute mate, maybe with an offset, this edge here. Other way. It seems like there's a 50% chance you'd get that wrong, but I find it actually happens every time. So at least 75%. And you can see that mates this to here. It's just a very crude example, but wanted to show some more common practice things. This is probably redundant to what Wesley's already showed you. Now we get into the design process, and this is one of my favorite slides coming up here, so get ready for it. We have all these things, right? These are the different steps of the design process. And I'm going to talk to you about how CAD interfaces with that. So starting off with the problem, you have to identify specific tasks that you can do. And you guys already did that. That's looking at the game field, deciding what points there are. And this is like, even before you decide what you can do, you decide what you decide what you want to do, you decide what you can do. That's very, very early. This is what you do on kickoff. You do very little of this and mostly this on kickoff, everything that you can possibly do, how matches will play out. And then you decide based on that, what weight do you want to give certain tasks? That's where you make your spreadsheets. You don't really want to start making sketches here, but you may want to make sketches just to test the viability of certain ideas, because it's impossible to actually think of the difficulty of a task completely agnostic of the difficulty of making a mechanism for that task. And then we have concepting round 1. So this is where you flesh out your ideas a little bit further. What I usually like to think here is come up with every possible way to do this, like do a lot of ideation, because then you won't miss anything. Most of the ideas will be garbage, and you'll eliminate most of your ideas. This is the sketching part, and you actually don't need to make this in-depth sketches for everything, just like very basic sketches. And then you narrow it down to like maybe 6 designs, maybe 3, 4 really, that you want to start translating into 3D. And you guys already did a very good job at that, actually. So you don't really need any lecturing on this part. Then we have concepting round 2, and this is right now where you guys are, which means turning your sketches into 3D. And this is usually going to happen in week 2 and week 1. You guys already sort of got to this last week, so you're ahead of the schedule. And then after this, you have prototyping, which is like building physical models to test certain things. One of the big, and these certain things shouldn't be just random, like, oh, does this mechanism work? Because, what happens when a wheel touches a conveyor belt? It'll move, right? That's common sense. You don't need to build a prototype to test that. Now you might want to test what conveyor belt material will move the wheel most effectively. Or in this case, I was like, okay, will the ground intaking actually work with just these wheels on the ball from the side? And can I do anything to make it better? So what I did was I, sketched this out, taking screenshots of Onshape sketches and then drawing on them with the snip and sketch tool in Windows. And I'm sure Mac has a similar equivalent. Is super useful because you can try out new ideas on top of old geometry. And this is like, a very shitty mouse drawing, but it illustrates the concept. And then I took 2 power drills, I put some pencils in them, and then I duct taped zip ties to it, or I fastened zip ties around them, and then I put little pouches of duct tape filled with nuts on the ends of the zip ties for weight. And you can see there that I'm holding them. This wasn't a game piece, this was a ball I had lying around my house. This was COVID year, so we couldn't go to school. But you can see that it shows, okay, yeah, these do pull the ball in actually quite well. And so that informs your decision. Your concept decision is like, mechanically, one of these may be viable. And if, there's sort of an if statement where like, if this concept can be made to intake reliably, then it will be better, right? Because this concept wasn't ever going to shoot it out the side very strongly, and we wanted to be able to do that so that the driver didn't have to align perfectly next to the ball, next to the goal. Then we get to the big decision. Decide on your concept and come up with like the first round of off-the-shelf CAD. And that's where you're using off-the-shelf parts. So like you can see there's VersaFrame here. These wheels are really real wheels, and they're the wheels that we just showed. And this one only had one motor. It was actually a really complex chain run that would use one motor to drive all four of these. But I was like, I wanted to toy around with the idea, but it was kind of, not going to work. So, and this being done in week 3, to be honest, for the build season, this is accurate. For ERC, you should do very little prototyping, and you should mostly make decisions based on your gut. Although if you do have a question, or there's some quick things you can do, like get a bunch of wheels and rub them against the cube to see which one sticks the best. Like that's a very quick example of prototyping that is a very important thing to test. And I wouldn't skimp on things like that. Then you get to your big decision here, and whatever you go with, commit. No half measures. Half measures and not committing to a design are what killed us in 2020. Well, actually, COVID killed us in 2020. But we wound up building a robot that we didn't decide on the concept for until like a couple of weeks before the competition, like maybe week 5 of build season, week 4, because everyone wanted to do a shooter, and the other half of everyone wanted to do a low goal robot that with a climber. And so we were like, which one's going to be more viable? And there was no clear like, okay, this one is what we're doing by anyone. So we wound up stalling for a long time. And then when we did get our robot, we didn't have any time to test it. So whatever you're going with, commit. A bad idea, a bad concept that you commit with from the start will be better than the perfect concept that you only have a week to build. And then you have your final CAD. So what's happening between here and here, you might wonder. That's design reviews, and we'll talk about that next. Design reviews are where you're going to show your design, present them to a couple of your peers, and to actually me and Tuni and Srinivas Andrea, and we'll give you some feedback. We won't pull any punches. We're not going to give you like feedback on tiny things that might wind up being learning experiences, but we will give you feedback on big things like that part isn't fabbable, or pick a wheel that's not $9,000 here, or this chain needs to be tensioned somehow. And this you can see is after design review. There was a point brought up in design review that was like, okay, but if you don't stop the intake perfectly, the ball's just going to fly out. And I was like, oh, that's a good point. So we had a flap here, and that flap was actuated by a servo. And that servo would move the flap up to 90 degrees or back down flat. And that would stop the ball from coming through. So it would be up while it was intaking and then down while it was shooting. And that worked really well. So yeah. And also, if you have design features like this, those are things that software can automate, and maybe get you the Innovation and Control Award. Definitely think about control in your design, though. And you can see this also has, different wheels. I used 3D printed wheels, and then you can see that the belts here, there were belts only on the bottom here, but here you can see there's belts on the top and the bottom. There's 2 stages of belts. There's a bunch of different design tweaks that you end up making during the design review. This hard stop being another one. And that's very important. And then you get to your robot build, where you start machining and assembling parts. So this backplate was machined. You can see the floor is red here. That's because I was doing it in my garage at home, which has a red floor. These blue parts are 3D printed, and they all went on 5mm hex shaft in bearings inside that wood. See, there's a slot for the flappy flapper. And then you want to do your robot testing, which is like, test your robot under actual use conditions. Give yourself at least a week to do this. Especially, I would give yourself 2 weeks to do testing, because testing and software blend together. You can see here, I made a cardboard cutout of what the goal looked like. I taped it to the end of my work table, and I put the robot on the work table and just fed balls through with the motors running at top speed. And I was running these motors at top speed with a power supply I have at home. You can do the same thing with a motor test board. So, it should be pretty easy for you to prototype whatever mechanism you have, as long as it's not an impossible mechanism. And you might wind up just needing to wait until software has code on the robot in order to do testing if you have like servos or things. But I wouldn't worry too much about servos unless you need like small actuators. Like it might be good for a gripper, you know, like one that goes like this, but a motor would probably fulfill the same function, and servos are way more likely to shred. So just think about that. And you can see here that this silver here is the duct tape belts. But I was really just doing a bunch of testing. I tested from different distances to see if my distance predictions were accurate. And I tested different gear reductions on these to see, you know, what shot the ball the best. I took slow-mo videos of it shooting, and I wanted to see what was going on because it didn't work like this originally. You can see here there's green tape up top on this one. And there's a bunch of other stuff going on. It was popping out the top. It was just shooting up the top, like directly upwards. And I was like, why is this happening? And then I had like belts falling off a bunch of times. And then I had like, you know, the ball wasn't intaking, so I had to mess with different speeds and different zip tie configs. There's like so much stuff that can go wrong that you just don't expect. And so you need to give yourself time to work through that. Does anyone have any questions about this slide and overall the design process? Because this is really big, and this is less actually what you came to the workshop for, which is how to CAD a robot, but there are some really important, you know, bits of information in here. Does anyone have any questions about that? Why does it have those grooves? Was that asked just now? No, it wasn't. Sorry, Justin. Oh, I answered that. I did not. Yeah, okay. No questions about this slide. Okay, sweet. Let's talk about design review. You'll present your ideas to experienced CAD members, and then you'll get some feedback and revisions. We're going to look at a couple things. DFM, which is designed for manufacturing. DFA, which is designed for assembly. So are all the bolts accessible? You know, can everything be held together? DFS, which is designed for service. That's an offshoot of DFA, which is like if your design breaks, how easy is it to fix? Because if you're at the competition and you break, that should not be the end of the competition for you. It should, you know, not limit what you're going to do for the rest of the event. So design clever ways that you can hot swap things. We also want to do a cost estimate. So like, is this design going to be wildly over expensive? And then some major optimizations, like removing certain features, adding motors, things like that. And then minor optimizations, like, you know, okay, this hole looks a little bit too big. Make sure your tolerance is good here for this bolt. You know, you want the hole to be a little bit loose fit, so that it doesn't rub with a shaft, or like, you know, you want to maybe pick a different wheel. Maybe you want to use a different type of belt. So these are what we'll cover in the design review. And this design review picture you have here was ERC last year. Wesley remembers this. What we did was we did a combined design review and concept decision. So this is what you see back here. That's this. I pointed to it. That's this. Which is we had two concepts, two pretty strong concepts, and we were deciding between them. And we sort of baked that into, we looked at the pros and cons of each design in design review, and then we were like, okay, we're going to go with this. And we had this whole thing up on a projector. We had a robot here for reference. It was pretty cool. So now let's talk about the nitty gritty. I've gone through a little bit of this so far, and this is the tail end of the workshop. There's 2 slides left. The nitty gritty is as follows. You have your structure and components, and this is pretty rigid. This is sort of what you have to stick to. So this is going to be tube construction, sheet construction, and superstructures and mechanism frames are things I want to talk about. You can't really make anything you want, contrary to popular belief. Your limit is not your imagination, it's what you can buy. Now you can imagine a lot of things based on what you can buy, but you know, so these mock-ups here, this was the Gary Team 47 CAD from last year. This was the final CAD. You can see that it doesn't have full off-the-shelf imports. It didn't need them. The mechanical members were smart enough to figure out, like, okay, we need 4 bolt holes at the bottom here to bolt it onto the back rail here, and these H-frames here for structural stability, they need to be bolted through the rear. So that's great. We're going to look at this robot in a second, and it also has some other cool examples of structure that I want to highlight because it did a very good job making sort of a complex system very frugally. So we're going to look at that. But yeah, you have these, you know, this is a 2x1 piece of tubing, and then you can see there's a little hole in here, and that's for a 12mm bearing, which is for 5mm hex shaft. If we look at this is our 12mm bearing, and you can see that we got our motor here. This is a core hex driving it. Wesley has this in his BOM. And the core hex spins very slowly. It spins at like 100 RPM, which is 100 revolutions per minute. That's about this fast. So spins there. We've got another gear reduction here. These are rev gears, so these are off the shelf. You can buy these. I would recommend probably not designing your own custom gears in this application, especially if they're interfacing with this 5mm metal hex shaft, because plastic 5mm hex bores will like turn into circles in like 3 seconds if they're under this kind of load. Because not only does the bucket need to raise and lower, but if this bucket gets hit, all that torque goes back into the motor and the shaft. So you got to be careful about that. And that's the same reason that we have these metal things here. And these metal things are 5mm locking hubs. They have a 5mm hex bore, and then they have a just thought of a boring pun. Um, they have a 5-bolt hex pattern or 5-bolt bolt pattern, and that bolts into the wood rather than the wood having to have a 5mm hex piece. And you can see these here are just 1x1 wooden dowels, and you can get those from Home Depot, and they're a great, super cheap structure. You don't need to use metal for everything in ERC. We don't use wood in FRC, but use it in ERC. You will like it's so good because you can wood screw things into it, you can glue it together. It's very cheap. It's not always dimensionally perfect, but these dowels are actually very good. Now you can see we have this shaft here, and we have a bearing on either end. And that bearing sits in the outside of this tube here, and that makes sure this shaft can rotate, right? Like the shaft is slipping in the bearing is fixed in the tube, and so the bearing rotates, and the shaft, it allows the shaft to rotate. And what's not pictured here in this CAD, but what was added by mechanical members were shaft collars, which you might have seen, you might not have seen. It's just a little ring with a set screw in it, and that screw clamps against the shaft, and that makes sure that the shaft can't move side to side. So it just, one on the outside of this bearing, one on the outside of this bearing, it can't move in either direction. And there were some shaft collars on the rotary arm mechanism as well, just to make sure that they wouldn't move. So I want to talk about how to actually do work with a mechanism. And you guys should have more context for this than you did at the start. But the most important thing is motors and servos and turning rotary motion into linear motion. Now, the graphic that I have here isn't great, but what it does show is that we have a motor here that's attached to a chain and a sprocket, and that spins this pulley. And now this pulley has ridges on it so that it grabs the duct tape belts better. And then it has an off-the-shelf wheel sandwiched in here because I knew that a 3D printed wheel wouldn't be grippy enough. And although 3D printing would have been way cheaper, these wheels were one of the major cost drivers of this robot. So I needed to reduce the amount that there were. And I actually wound up just taking the drive base wheels off for this. And then there was this flange on top, and that was for, keeping everything together, keeping the top belt on. So yeah, this motor mounts here, it spins this, which spins this, and then the linear motion is the belt that runs along this. I haven't given an example. I mean, this example is another example of doing work with a motor, right? You have this motor, which is geared down so that this, arm spins pretty slowly but very strong, very accurate to position. And then it just rotates this rotary arm. That's another example of doing work with a motor. That's the end of my That's the end of my slideshow. Do y'all have questions specifically like pertaining to your CAD projects? And do you want me to go through a very quick design process of like sketch to CAD?
I think the sketch to CAD would be helpful.
Okay. Any other votes for sketch to CAD?
Yeah, same.
Okay, let me get my sketch pad out. Well, this is actually, I drew this concept during math class the other day. It's for a belt only elevator. Um, and I'm wondering if we should CAD that. Probably not today. But let's go. I'm going to do a CAD concept for ERC last year. So ERC last year had to actuate a ball. And let's do a pretty simple concept. Set up a document camera here. Let me just join the meeting on my phone pointed at the ground. Okay, can y'all see this? Okay. This is incredibly janky, but I just want to illustrate a little bit. Let's see. I wonder if I can zoom in on the camera. Oh, my little thingy isn't working. Okay, I'm just gonna go back to this, and we'll do it sideways. Let's see, like this. I want to sketch big so that you can see. So grab my pen here. What are we doing here? Do you guys have any requests for mechanisms for MIDI CAD? And don't say one of the ones that you're already working on.
By mechanisms, do you mean like an elevator or what?
Yes, something like that. Like, give me a concept. Like
Yeah, that
conveyor
I
belt.
think like I did want to see the elevator.
You want to see the elevator? Okay,
Yeah.
let's do a very simple elevator then. And none of you guys should do an elevator because it's going to be janky. So I'm starting off with just a line here. I'm going to draw the base of my robot. And then I'll come here. This is just going to be a front view. So I've got my elevator here, and I'll need some uprights for the elevator. I'm going to switch to this pen. It's going to show better. I'll need some uprights for the elevator. And then probably on top of that, I'll need, and then I want to represent the wheels here just so I don't have anything that conflicts. So the wheel is going to come up here and then come down here. It's going to look something like that. And I'll do that on the other side as well. And trying to get dimensional consistency at least. So I started on this graph square and I'm going to this graph square. So the wheels sort of look the same on both sides. And then you can see it's like 3 blocks over is where I'm starting the upright sketch. So I'm assuming these are 2x1 uprights, right? It would go like this if you had it in an isometric. It would look like that all the way down. And I'm going to actually do a quick ISO. So something like that. And I think the concept I had in mind was one that used a pulley, and then instead of having any linear motion slides, like usually when you have an elevator, you have your fixed stage here, and then you have your moving stage. And these squiggles just indicate that the thing is cut off. And the moving stage has bearings that have to go out here. Wesley's familiar with this because he designed one this summer, and we're building it right now for the returning member project. And then you also have a bearing here so that you limit both side to side motion and so that you constrain up and down motion, right? So that you can only slide this way or this way. So that's great. Bearings are expensive, and God, this is really. I'm gonna go up and show you guys what I just drew. I need to get a better document camera if I'm going to keep doing this. Let's see. Oh, ignore the carbon fiber tube here. And my passport. And the rubbing alcohol on my desk. We'll keep going with this mechanism concept. So I think I'm going to do like if you think about it, the edge of a pulley, like this edge moves up and down too. And it's not flopping around really that much. Belts, a belt is pretty strong. So if we have this pulley, it should be pretty strong. I'm going to sort of draw a pulley up here, pulley down here, and then I'll do the same on this side. And this mechanism, let's say this is going to be a mid-goal elevator, because you need to do a 2-stage elevator if you're going to go for the high goal. So we're just going to go mid-goal. And then these pulleys will have a belt that comes off of them. Assume they're the same size, in real life. These ones are, but the ones on the right aren't. And then let's just design a little clamping mechanism to clamp onto this, and then sort of this center carriage that's going to run up and down. And that's great. This clamps onto here. You can't see these tiny arrows I'm drawing, but we've got a carriage, and then maybe we'll do some kind of very simple, intake, it would be like this. And I'll just mock that up when we're doing it. And maybe the circles would be on top and the bottom, and those are wheels. And it's important to also think about where motors might be. Usually when I'm sketching like this, I don't think about motors, but it's sometimes important to consider that, especially when you have a complex scenario. And these pulleys have to spin opposite directions. And I think the best way to do that is going to be an infinity belt. Super simple concept. We have it on our robot this year. It's an infinity belt. And I think we can put the motor behind this right here. This will be our motor. But I just colored in black there. And I'm going to make a quick ISO of this robot. I usually start with a drive rail for my ISOs, and then I'll go up with the upright. Now this is where I wish I had my erasable pen again, because it's useful for this kind of stuff. And again, sorry if you can't see exactly what I'm sketching. So now we have these uprights here, and I'm going to draw the pulleys. They're probably going to be on the back here. Now circles are hard in ISO, but you just have to remember the direction you're looking from. So it's going to look something like this. And they don't need to be perfect representations. They really don't. And I'm going to go with big pulleys, because a larger, actually you don't really need to. Never mind, I'm not going to do that. And then you'd probably want some sort of timing belt for this, because timing belts, like, they have grooves and they have teeth in them, and so they'll interface much more consistently. I mean, you could do duct tape belts, but that just makes the viability of the mechanism depends on the stiffness of these belts, and timing belts are way stiffer. So something like this, and you can see we have our belts represented, and then I'll have our little clamping carriage here represented in 3D as well in ISO. And now this isn't my best drawing by far, but it does enough to show the concept. And then we'd have, I'm going to go with a wheeled intake because I've been a fan of that since day one. And you can see here I've got my carriage on there, and I've got a wheeled intake on it. And I'll just finish this off with just a back rail. So it looks something like this, and our wheels are here and here, like this. I'll do some shading on the fronts of the wheels, give them a little depth. So that's sort of the robot concept sketch. And it may be difficult to see, but it'll be much easier to understand in 3D. So let's do that now. I'm going to kick this fool from the meeting right now. Actually, I'm just going to unpin his presentation. Okay. So now it's time for CAD. I got my import example here. I'm going to go back to Onshape. Demo workshop. Your elevator example. So I'm going to start first, and you guys may not be able to do this, so that's worth considering. I don't think you will have permission to import from other documents. You go to My Onshape. This is a super useful thing to do, but I heard some of you guys saying that you didn't have perms to do this. So what you would want to do is just say game field and KOP chassis, and then you would just click KOP chassis here. And it's been versioned. Create a new version every time you want to import it. Then we can go to assemblies in this, and I think it's full assembly, if I'm not mistaken. and we'll wait for this to load for a second. Now the thing about Onshape and multi-document interaction is that with multiple documents, you need to have you need to version it every time you make a change in the other document. Okay, so that imported that. Great. I'm going to anchor it because right now it moves around freely. So we're going to press mate, and I'm just going to use the bottom of the belly pan centered here. And I'm going to click the origin mate connector. And I'm going to call this anchor. So now this won't move around. And then we have our, I'm going to name this full assembly. Should have also said says full assembly, but you know. And we've got our mechanism. So I'm actually gonna delete this Part Studio. I'm gonna show you something cool. If we go up to the top here and click Create Part Studio in Context, and then we select Origin Mate Connector, brings us to a new Part Studio that's in the context of the assembly. This is super useful for rapid prototyping. You have to be careful with context though, because let's say I make a sketch. If I click this and make a sketch on this, you know, and I use my project tool here to bring a bunch of these existing geometries into the sketch. You know, I can bring geometries that are on the plane, or I can actually bring this line here onto there. If I finish that sketch, we have our context, right? It's in context. But let's say I go to this assembly and I delete that belly pan. All of a sudden, the whole Part Studio breaks. So you have to be very careful when you're doing this because, well, it's great for a demo concept. You want to avoid context when you're doing actual mechanism CAD. I'll say that. So we have our initial. Which side do we want to be the front of the robot? I think probably. Yeah, we want the most of the weight to be over the front two wheels because then it won't wheelie. I think if we put it over the back two wheels, plus there's less room here, but if we put the elevator over the back two wheels, it can drive these so it'll wheelie. Here it'll just slip the front wheels more often. So that's a quick design decision we'll make. And I can go ahead and just start a sketch here. I'm going to say upright 1. I'm going to name this sketch uprights. Yeah, that is poorly done. And we'll go ahead and, you know, project this bit here, right there. And we'll go ahead and make ourselves a 2x1. I clicked G there to make myself a 2x1. And then, how tall should it be? I mean, the frame perimeter is 20. Let's take off an inch for that, so 19. So now we have our thing here, and I'm going to do some quick sketch prototyping, actually. Hold on, give me 1 second to mirror this. I'm going to mirror it about the middle plane here, and I'm just going to select all here. I'll click this and this too. Okay. Now let's make ourselves a little rectangle here, and let's constrain the height of this. Hold on, I'm going to make this a construction geometry. Just pressing Q and G does the trick there. And then I'm going to make this like 4 inches tall. See, if you think about it, the taller this is, the more stable it will be on the belts, but also the less travel you have because you reach the top sooner. Right, so we can play with that. And I want to see, I mean, this can move up and down in the sketch here. And I want to represent our goal. How high is the goal? Do any of you guys know off the top of your head how high the mid goal is?
10 inches.
Is it?
Yes,
10 inches.
and high
Okay.
is 20.
Sounds good. So we're gonna make ourselves a quick, another quick thing here. And I'm going to dimension it from the origin at the bottom so that it's on the ground where the wheels are. And sketch prototyping like this is also a very good way to, see, it's like 0.75 if I recall correctly. Something like that, yeah, okay. And 10 inches tall. So what I'm seeing here is that we honestly don't need all this reach, although it might be nice if we're stacking later. So I think probably 4 inches is fine. We might even want to go up to 5 or 6. Or we could do little extensions here. But this was just to test the viability of this geometry and see, okay, can we make these shorter? Maybe we make them both 18. Or maybe we make them 16. Right? And then that can still reach here. It can still dump into the box. Just going to dimension the bottom here. It's bothering me. I think it's 24 wide. But I think we'll just make it 19 because going up right up to the frame height limit gives you some room to breathe. And let's do a quick dimension here. This from the bottom of the floor here is 19.75. That's going to become a driven dimension, 19.75. And that tells you the legality. So if we go 18 here, it's 18.75. The tallest we could do is 19.25. But we don't want to push it that much, really, because you would hate to get called at inspection because of something like that. You want to optimize, but you don't want to, give yourself future risks. So I'm happy with the way this driven dimension is right now. So because we have done all these sketch prototyping components as construction lines, the only things that we're actually going to extrude here, if I just press extrude, it'll extrude the 2x1, and it automatically goes to 1 inches. Awesome, amazing. We have our uprights. So the next part is going to be the pulleys. Now, I think, yeah, we'll need to. So there's a pretty bit of a crossroads we're at here. Is I think we can do either a pulley here up top. We always want a pulley up top at the very highest point, and then we could also do a pulley. We could either do a pulley at the bottom above the rail or a pulley through the rail. Because the thing is that when you do a pulley, I'm going to screenshot this and draw on it a little bit. So I'm going to stop the screen share and share my entire screen. Let me share my entire screen here, and we'll do some drawing on this. So we could do, if we have a pulley here like this, right? This, I mean, if it's just, touching the bottom, the only usable part is like right here. And that limits our ability to go down quite a bit. And we want to go pretty far down because we want to reach the ground where the cubes are. Right? The cubes are on the ground. They look like this-ish. I'm going to erase that. So maybe we want to move the pulley down here so that it's almost at the bottom. But then you come to a bit of a trade-off of like, okay, can you actually take that apart? For machining this, you have to machine 2 holes through tubing instead of 1. The reason I picked aluminum 2x1 for this, by the way, is that it needs to be stiff, it needs to be dimensionally accurate, and it needs to be easily manufacturable, and 2x1 does all 3 of those. If you did wood, it might be floppy and it might be unstable. If these belts are moving relative to each other, the mechanism might not slide up and down so easily. And if it gets hit, you don't want it to snap in half. This is your critical structure. We may even wind up adding some components to support that structure. But yeah, so do we do a pulley here or not? Or alternatively, do we want to do we could do something entirely different. We could delete this front rail here, and we could do just bolting these to the sides, and then have the thing be on the front, and that way the intake can come all the way to the ground. I don't know that that's necessary though, because the cubes are 6 inches tall. I'm gonna go and mock that cube up. Actually, I'm just gonna give myself a mock-up cube. Let's go ahead and. Did I say something about the back of the uprights? What did I say?
No, I'm asking, like, couldn't you just move it to the back of the uprights?
Could you move the pulleys to the back of the uprights?
Yes.
But that's where I've always intended them to be. But what I'm
Oh,
saying
okay.
is
I
that
thought they're on the front.
what I'm saying is that your intake can go down lower because it's sticking out. It has to stick out. Your intake can go down lower if this front rail doesn't exist. I'm going to offset this plane. It was 0.25, we said the ground plane was, and I'm going to name this ground plane. And I think it needs to go the other way. And this is where I'm going to sketch the cube. I'm going to drag this out here. Whoa there, buddy. Someone's not happy about my existence today. God damn it. There we go. Sweet. So I'm going to make that ground plane wider just so I can see it. And I'm going to sketch on it. I'm going to make a quick little cubey. Drag it out from here. I'm going to make it 6 by 6. And then I'm going to extrude it up to 6 inches. Oops. There we go. There's a little cube. So I don't think we'll need to have our front rail delete because it looks like we can just grab onto the top of the cube with whatever intake we have. So I'm going to go ahead and hide this part. And now I'm going to start making our pulleys. And this is Crayola CAD, so it doesn't need to be super advanced. I'm going to make a 12mm hex hole. And I'm going to put that 1/2 inch up so that it's halfway through the front rail. Or sorry, 1 inch up because the front rail is 2 by 1. And we can honestly mirror that feature across the center plane here. And then let's look on Rev here. Let's see what sort of 5mm hex pulleys they have. Let's see, just if we look up pulley. Bad typer. Okay, we got round belt pulleys. This is probably what we're going to want right here. That's the money. And then we've got our belts, and we'll use Onshape belt calculator in a second here. So this is a GT2 pulley, and we have our 12, 24, 30, 36, 48, and 60. And we'll want to use the same two, and we'll probably want to use a pretty big one. So I might wind up downloading and importing the, let's see, I think we'll do, let's play it by ear. I'm going to use the, I'm going to make another circle up here. And I'm going to start speed running because I don't want to waste y'all's time. But if you do want me to slow down and show anything, then tell me. Okay, so now we have our holes. I'm going to use Onshape belt calculator, which is a feature script I have, by the way. If you want to add feature scripts, click over here and click add custom features. Pulley 1 position is going to be this. All right, now low. Pulley 1 position is going to be this one. And pulley 2 position is going to be up here. And we'll see if there's even a belt that's this tall. Yeah, so 180 tooth seems to be the longest one you can get. We may wind up having to do chain here. And chain will probably also still work, to be honest. With HTD, we can get all the way up there with HTD belts. So we may want to just choose that. But 200 tooth belt, I mean, that's expensive. This is a 184 tooth GT2, and that's $10 for a belt. But you get HTD belts from Vex. I'm gonna search that up. See what we get. Here we go. HTD timing belts. So 250 tooth is the longest they have, and that's really big. But okay, 200 tooth is $15. That's not terrible. You just have to remember that, you know, 2 of those is $30. You're spending, you know, half your budget on belts. But if we look at if we look up here, and also you may want to consider that these pulleys, they will be like you can't use these 5mm hex pulleys if we're doing HTD because that's a different tooth profile than GT2. And if there's no GT2 belt, then we can just, you know, we'll have to find either an insert that adapts 5mm hex, or we have to do a printed part with a bolt circle or something. But we have those inserts, remember in here, this one right here, those locking inserts may work. I'm not going to get that detailed in the CAD today. Let's see, 200 tooth belt, it's pretty close. What if we go with a, let's see, let's do next smallest belt. Okay, that's a little smaller, 180. What's the cost of the 180 tooth belt? $13.99. Save ourselves $2. I think that's worth it. Is it worth it? Yeah, it's totally worth it. Okay. And I'm going to copy this value here. And I'm also going to have it make 2 pulleys. So I'm going to say custom pulley and custom pulley. And then it'll generate those pulleys. And if I offset it by like 1, go ahead and offset it by less than that. 0.5 should do the trick. Yeah, so that's great. And we copy pasted that value, so we're going to go, you can see this is red right now because the holes that we told it aren't the same length as the holes that were there. So I'm going to delete this dimension here. I'm going to dimension this hole to this hole. I'm going to paste in 15.354, which was the value that the belt calculator gave me. And that'll go apply to the other side because I mirrored everything. And now you can see that we've got this. Fantastic. I'm going to hide these mate connectors because they're annoying me. Actually, it's not quite perfect, is it? Ah. Oh, because I clicked next smallest belt. So we got to go closest belt again, and then it'll rectify. Okay, sweet. I'm going to hide this. So now we've got our belts and pulleys. You can see this is a 5mm hex shaft. I'm going to go ahead and click this, and I'm going to make it bright cyan because that's the printed part appearance, and I don't want to forget that these are 3D printed parts. In addition to that, I'm going to go back here, and I'm going to say enable belt teeth because I think we're probably going to wind up creating a device that goes into those belt teeth. Let's think about this. We may wind up wanting to have this belt go farther than the side. So that's worth thinking about. You would need bigger pulleys and a longer belt. I think we can probably still clamp it on without doing that. It'll just be a little bit different. So I'm going to quick design a little clamping block that we'll just clamp onto here. We'll do a square here. And then I'm going to come up with, I'm going to copy a bunch of these tooth profiles. And hopefully this block will just like slide onto the belt. And then we can use it to, and this is a very arbitrary thing. I'm just Crayola CADing this. This is levels of detail that you don't always need in Crayola CAD. And I'm going to make this this distance from here to here. I'll make it like 0.25, and this height, I'll make it 1 inch. Okay, and then I'm going to dimension this. Let's see. I'm going to convert this, project this onto the sketch in construction form. I'm going to dimension the center of this circle to this just because I don't like blue stuff, and blue stuff is annoying. There we go. And that gives me that profile. I'm pretty happy with that. And then we'll have, this will be a 3D printed part or something. So tell you what, let's just, this is a very arbitrary design, but I'd probably spend more time doing this in a clever way if I was doing it this is only 1 inch tall, isn't it? We can make this 2 inches tall. And we'll make this, I mention this. I want this to be like a tube plug, so I want it to go in the end of a tube. Point. And then we'll go ahead and just gonna select this whole ass thing. And it should project. Come on. It decided it didn't want to. Okay, and I'll extend my line. I don't know where I did my line, but I'm just going to write it again. Okay, and now I can extrude this. It's going to be really weird. Let's see what it does. Okay, so the whole thing, I must have projected the outside at some point. I'm just going to delete this because the whole thing was projected. Ah, you know what it did? It did that. Okay, that's weird. Can I just click that? I'm going to click this. That. You know what? I didn't have a projection of this line here. Oh, I clicked the wrong feature. Okay, sweet. I'm going to extrude these two and this. I'm going to extrude all of these up to this face here. And then I'll extrude them even further. The size I want. You wouldn't be gluing it. It would be two parts, and they're clamped together. So this will bolt together. Sorry if my concept isn't coming across very well. Just doing it very quickly. Yeah, the idea is to have it be a clamping plate. I'm going to continue showing this. I will have to extrude this, and I'm going to just do click every single one of these. It's going to be annoying, but I'll make it happen. And this isn't the way I did the sketch. Sometimes that's just the way it is. Add it to this part, and we're going to go up to the same face. And now we have ourselves a base block, and then we'll make, so the belt is actually just going to slide in here. So I'm going to leave the negative of the belt. I'm going to hide this part. We're going to leave the negative of the belt. So if I extrude this, and extrude it, that seems pretty good. And then we'll add it to this part here. So the belt should just slide in here, and if the tolerances are right, which they're definitely not right now, you would need to probably print this and then retry it in order to get the tolerances right. It would sort of work out. And this is going to be a 3D printed part as well. And then I extruded it 1 inch out. I'm just going to do a quick little offset on these faces here, making a construction line to mirror it across. And I'm going to go 0.1 here. And that's going to be to remove this so that it's actually a little tube plug. There we go. Okay, there we go. And now we're going to extrude this, remove. Okay, now we have our tube plug. I'm actually going to extrude this. I'm going to mirror this tube plug and this belted pulley across the main plane here. Entities to mirror this, 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 and this. And you can honestly have just done one upright to start with and mirrored it across that. And I'm going to click the right plane here. And that'll give me another set of parts. And we'll make those new. And check this out. This carriage. Actually, you know what? I don't even need to make a sketch here. This is just, I'll muck up the 2x1 tubing like this. And I'll go up to this face here. New part like that. Boom, 2x1 tubing. And this is sort of our carriage. Let's go ahead and make ourselves a little mechanism here to act as our intake mechanism. I'm going to make it on the bottom of this. And probably for the carriage, you'd want to have like 2 of these. So we could do a, yeah, let's do that. You could always just make these parts really tall, you know, so that it really meshes on there. And then also this is sliding against the 2x1 metal. So it would be sort of a rough action, but I'm going to make this aluminum colored. It'd be sort of rough sliding. You got to go in? All right. See ya.
Yeah, thank you.
Yeah. So I'm going to make the intake really quick, and then we'll be done with this. I'm going to unhide our cube here. We have it right there. And I'm going to, again, make this out of like maybe 1x1 tubing. Not 1 inch long. We'll have to make it like, it's a 12-inch extension limit, right? So we'll make it like that, sort of. I'm going to dimension it. I'm gonna put a point here. Actually, I'll just do a circle. And I'm gonna make a big construction circle that is like 2 inches. And that'll give me a mock-up of a wheel, because I don't want to do it based on where the tube is, I want to do it based on where the wheel would be. But this 12mm hole is for a bearing here. And then I can go ahead and dimension the edge of this. Actually, I'm just going to mirror it first. You use mirrors a lot. It's like super, super useful. Because a lot of the stuff you make is going to be symmetrical. So this should be 5.5, let's say. We want to give them a little bit of compression. And you can see that that's just about rubbing through here. So we may wind up needing to do like a step where it goes offset there. And that might wind up making it more of a candidate for plywood, potentially, because we can do a different geometry with that. So let's go ahead and just say, you know what, this is, I'm going to make this shorter, by the way. I'm going to make this like 10. It doesn't need to be 12 inches long. And I'm just going to make this a line here. This is going to give us a lot of freedom, actually, this decision to make it plywood. I'm going to dimension this like 5 inches from here, so it can really suck the cube in. Dooney's gone. If y'all are getting bored, tell me and I'll stop, but you did request this, so. I'm gonna make it 3/8 thick because plywood is, it's a good thickness for it to be. And this is sort of a part that I would say like in a design review, like, oh, you shouldn't do this, it's gonna break. So keep that in mind. Let's see. I'm gonna do another line here. Working in the context is sometimes hard because you can miss certain stuff. Say, okay, there we go. Or you can like, sometimes it's hard to navigate to exactly what you want to see. I'm gonna just dimension this a pretty arbitrary distance away, and I'll add a chamfer or something later for strength. Sweet. Okay, there's our part. And we'll make ourselves, oh, we can add the wheels from MKCAD or something. So this is our elevator. I'm gonna, and this was all made in one part studio. I'm going to insert all of these parts into our main assembly. Wants me to select stuff to insert. I guess that wasn't. There we go. There we go. So now we're in our assembly. Everything's there. You'll notice though that nothing is constrained or dimensioned. This is for a Crayola CAD. I'm just going to group everything. Should tell you what, I'll just click from here. So boom, boom, boom. This and this and this. And I'm going to pick one item from the drive base to group it to. That way it just stays in place. And grouping isn't a super great solution, but now it doesn't move. So we take those. And I'll also group this. I'll call this carriage group. I'm going to mate that plywood gripper onto here. Now you probably could have made that out of aluminum, and it may or may not work out of plywood. This is something that you'd have to like get a feel for in real life. And you'd also need a place to put a motor on this. So I think you'd probably want to put the motor somewhere around here and then run a chain or a belt and then some sort of way to invert it. But now we have this. I'm going to mate. Let's see, I'm going to mate this thing right here to the top of this and give ourselves a little slider relation. Call this slider. And the nice thing about sliders is that you can set limits. So our limit can be a minimum distance of like -1 and a maximum distance of like -1 is maximum. You always have to think of like minimum. Yeah, there we go. -18. -2 maybe. Yeah, that's pretty good. Okay, and let's see what the limits. Okay, that's too far down that it can go. So just gonna go in the slider here. I'm gonna set the limits back to what we want, maybe like 14. Let's try conservatively. You can actually animate the degrees of freedom here. Let's see how far down it goes. That's pretty good. Okay. Oh, there we go. So it can go up to there, down too far. Let's go like -12. Oh, it didn't, it must have not corrected. We'll go 2 inches further down. We can support that. Sweet. Okay. So this is our mechanism. Now we need a motor to drive one of these and some sort of modified pulley to going to make that 13.5. Give ourselves a little bit more clearance. And we need some sort of modified pulley to give ourselves that, that infinity belt that we wanted. I might make that really quick. You can see we're not in the context anymore. If we ever want to go back into the context, you just do this. But I'll make ourselves a little, honestly, I'm just going to extrude this outwards. And then we can go ahead and, what's the best way to add a revolve feature to this, like a groove in it? We probably want to make a plane. Yeah, I want to make a plane offset from this, because I know this is 1/2 inch, and I'm going to offset at 0.25. And that's the center plane. I'm going to make a sketch on that plane. I'll project this onto the sketch, make ourselves a little circle here. And our belt is like, our poly belt here is going to be like, yeah, something like that. Okay. And then make that 0.25 away. We'll mirror it across this middle line here. Actually, you don't even need to mirror it. You just need an axis to rotate it about. Make that vertical. And then we'll go ahead and revolve this. Remove, revolve axis, this, merge scope. That's brilliant. Okay, now we have ourselves a little pulley. And we can mirror those features. So if you click feature mirror here, because we already mirrored the part, we don't want to have to do that. So I'm just going to click revolve, sketch, and plane. And the mirror plane is the middle here. And should work. Oh, we need this extrude too. I'll tell you what. This extrude doesn't need to be mirrored as long as we just go back into this extrude and we also select this face to extrude outwards. We've got to update the merge scope so it merges with all, and that should give us, we got to update the merge scope of this revolve as well so that it hits that. Boom. And then we could make a little infinity belt. It would just look like woo woo. And then we'll have to make a motor mount offset from there. I'm going to open up MKCAD and we'll look at HD Hex. So this has turned into a 2-hour meeting. I got nowhere to be, but here we go. Yeah, this has turned into a 2-hour meeting. I got nowhere to be, and hopefully this has been helpful. But I'm going to end the CAD process here. You would want to have probably a plan for how you would. Now I always wind up when I'm doing Crayola CAD. I'm gonna offset this by like that much, just enough for a mounting plate. And then what you'd probably do is you'd bolt this pulley on here, and then you would have just this pulley free spinning on a shaft, and then you don't really need to worry about any sort of hex shafts because the hex shafts aren't ever driving the pulleys. It's this motor. You'd probably want to make like a little plate that goes up to the belly pan down here, and that would mount the motor. And yeah, boom, you got your mechanism. And something like this for a wheel. This is what I was envisioning originally. I'm gonna fasten this here. Actually, I'll make it a revolute, just for funsies. And then what I can do is a replicate, and I can match edges on face. This face, and this face. And that'll put wheels all the places I want. And then I'd probably also want another motor, maybe up here. and that motor might. Actually, tell you what, I think we should do the change configuration 90-degree output. That way we can lay it flat, and that way it'll package a little more cleanly. This 90-degree output is like, it costs money though, so you'd have to budget for that. This mechanism probably winds up being over budget, I gotta say. I mean, it's close, but like. Okay, so we should put this actually on the underside. This is just the center mate connector here. It's nothing fancy. Now this will also restrict how far down we can go. Not by that much though. But yeah, anyway. This is the mechanism. This motor would probably wind up spinning like a shaft, and you could have a chain going to this one, some sort of gear to reverse it, and chain going to the other wheel. It's a pretty simple design. Okay, so actually I'll do one last little fun trick here. I'll play with my offsets so that it's like 5, and then -2. Sweet. Now it's got the cube. And probably if you were doing this, you might want like a limit switch or something on here, switch back here so that the robot could sense when the cube is in it. But yeah, that's that. Okay, now is the time for questions, and then I'm going to end the meeting because it's been almost 2 hours. Y'all are welcome to leave now if you want. All right.
Thank you.
Yep.
Thank
See you
you.
later. Let me know if you have questions during meetings. See you guys.
This has been really helpful. I didn't know you can offset a mate connector.
Oh, you didn't?
Yeah,
It's super nice.
Yeah.
Okay, I'm gonna stop the recording.